Okay, so how can we change this to my laptop?
Okay, it's already connected?
Yeah. Okay, so this is my last lecture, and what I wanted to talk about is the applications to high redshifts of the things that I've been discussing before. So before entering into the main subject, I would like to address again the same question that I wanted to explain to you before, and I wanted to do it better. So the thing is that you should be amazed, actually, because if you plot the mass accretion rates of the halos as a function of the halo masses, it looks very similar to the star formation rates of the galaxies as a function of the stellar mass. It's interesting that the slope of this relation is very close to the one that we observe with the galaxies. And actually, both look like a power law. And also, they increase as a function of redshift. Both increases as a function of the redshift. All right, so this is the intrinsic scatter of the relation. And this is also the intrinsic scatter of this relation, which is the next point. And the next point, you should appreciate that halos predict that the dispersion in mass accretion rates is around 0.3, something that we also observe with galaxies. And the point is, if galaxies form and evolve in dark matter halos, there should be something intrinsic in the galaxy formation from the dark matter halos. So the idea is, if the power law that we observe in the mass accretion rates reflects something about the star formation rates, is this scatter that we observe in the mass accretion rates of the halos reflecting something in the scatter of the star formation rates? To prove that, or try to understand that, I just developed a very simple model where you have here the reference, and you can consult all the details. But the main idea is that if you assume that this interface between the model and observations, which is the stellar to halo mass relation, is a time-independent relation, basically you can derive analytically what are the predicted star formation rates. And the point is that all the galaxies in the simulation will evolve around this relation, which might be not so true, but you can actually model the evolution, which I will explain later. So the main point here is that if you assume that this is time independent, actually it makes a very straightforward connection between the star formation rates and the mass accretion rates. And the star formation efficiency is just given by the slope of this relation. So then when you play that game, you see that the specific star formation rates as a function of the redshift for different stellar masses resembles to the observations. So here the points are more recent observations. The orange line, it's older observations. And older observations, we know that they tend to measure higher specific star formation rates just because they were overcorrecting the star formation rates by dust. So we know that. And now the new observations with better methods and techniques, they predict that they look like power law for the different estimators that I used here for predicting the specific star formation rate. So this makes a very powerful model. Also, you can also predict the scatter, and we see that is more or less the same amplitude of the intrinsic scatter. So this makes a very powerful model because if you have an observation at redshift 0, which is the stellar to halo mass relation, and then you use the mass accretion rates directly from the simulations from the merger trees, you can mock up your universe, no? So then you can calculate things like, for example, how many stars, what is the rate of stars that you are creating by megaparsec cubic as a function of the time, which is the star formation rate density, and it's showing here. So the main point here is that, so we have the observations, which are the field circles with error bars. We have the fit into these observations, which is the red dashed line. The blue dotted line, it's a new inference of these observations, correcting by this problem of overcorrection by dust that all observations had. And which we note that decreases. But the main point here is that with this very simple model, you can create this curve. Unfortunately, is that we don't know what is the mass limit that observation uses in order to create this plot. Just because they are always looking to the light and they are not looking to the stars. So here we just showing what are the limits of, if we take some limits of integrations, what are the resulting curves, okay? So you can say, well, your model looks better if you take 10 to the 10 or 10 to the 9 in some cases, for example, at the redshift. At 10 to the 10, it looks much better at high redshifts. Also, we can predict the population of galaxies. So here we are showing the galaxy stellar mass function as a function of redshift. And here the symbols are the observations, which is a really good match. But then you can say, well, why don't you just relax the assumption that this relation is time independent and then see what happened. Actually, this is not a new idea. This is an idea that is being applied. So the idea is the following. This is a very good schematic version of what I wanted to explain today. So you have here your interface, the stellar to halo mass relation. You can choose any relation that you want. So then the idea is that you will feed all the halos with this relation, putting galaxies on all these halos, follow the merger trees in the simulation. Remember the movie that I showed where you can see how the halos are forming. So actually you are putting all these galaxies in the halos. Then you calculate observables. One observable is the galaxy stellar mass function. The other is the star formation rate, and the other one are the specific star formation rates. Then the problem is, how can we compare these observables, these fake observables, to real observables? The problem is that real observables have a lot of problems, have systematics, have errors, and so on. So the thing is that if you know at least how these systematics and errors work, you can mock up these errors. So this is the next step, which is shown here. And then you compare to observations, and you make a chi-square, for example. And then if your model failed, you repeat again, and you repeat this process by doing Markov chain Monte Carlo.
Sorry,
Uh-huh.
I'm going to ask you a question, but I really haven't understood how you use a Markov chain Monte Carlo to go back on to. Because there's a part of the investigation process where well, model set of data, and then use of MCMC to.
The point is that you don't know what is the in your first step, you don't know what is the best model, right? So you just suppose any model. So let's make an example. So the first step is choose your stellar to halo mass relation. So then let's say that this is halo mass, stellar mass, okay? So let's say that you choose a stellar to halo mass relation which is a straight line, which is wrong, okay? So then you go through all this process and then compare to observations. And what you see is, for example, let me take just one observable, this one, the galaxy stellar mass function. So at redshift 0, we see that the galaxy stellar mass function is something like this with the error bars. And then from UMOC, you see that it's something like this. It failed, no? So then you need to look for all the possible best fit models, no? And that's where you need the Markov chain Monte Carlo. Uh-huh. Is it clear? Mm-hmm.
I have a question regarding the errors.
Uh-huh.
I didn't get it very well how the chart says applying effects to simulate observational errors.
Uh-huh.
I mean, you're just taking the observational errors and trying to simulate within these relations.
I will explain more about the observational errors at the end of my talk. But the main point is the following. So, for example, we know that different initial mass functions results in different stellar masses. Okay? So in that regards, it's applied effects to simulate. Okay? But I will explain more in detail. So this is basically the summary of all the fitting process. So you take your observables, which are the galaxy stellar mass function. You take the other observables, which are the specific star formation rates, and then the cosmic star formation rate. So here I'm showing the best fitting models for this particular paper. Yeah, the blacks are the data. It's the same data that I showed in the previous figure. And here the arrow bars are also the data. Actually, if you remember, when I plot the specific star formation rates, they also look like power laws. And this is the resulting stellar to halo mass relations. So if you see, the stellar to halo mass relations, they go from 0.1 to redshift 8, actually from redshift 8, which is kind of amazing. And you see that if you draw a line around all these relations, it's basically the same relation. No? You cannot say that it's evolving. And you can do things that are very cool. So for example, here, I'm plotting the halo mass as a function of redshift. And here you are seeing how the average dark matter halo is assembled. Okay? This is the meaning of the lines. But then we are color coding with the specific star formation rates. So then you can start to get some insights about galaxy formation. You can say, for example, that most of the star formation rate occurs in very high mass halos and a very high redshift. This is interesting, no? Because this will put a lot of constraints in our models of galaxy formation. The figure that I'm showing here shows basically the same, but what I wanted to show you is that in this paper, they use another observable. They don't use star formation rates, but they use correlation functions. They combine galaxy stellar mass functions and correlation functions, and they get basically the same answer, which is kind of amazing because it doesn't have to be like that, no? Why it has to be? Okay, and because this is my talk, I will also present my own work. So here are the galaxy stellar mass functions. In this work, I'm going from redshift 0.1 up to redshift 10. And here I'm plotting a lot of star formation rates. This is actually preliminary, so don't take it like the last word. Here I'm plotting the star formation rates as a function of redshift with the most recent data, which is a lot, as a function of redshift and the masses. And the solid lines are the best fits to the model. Don't pay much attention to the blue lines because this is on all the observations. And these are now the stellar to halo mass relations. Actually, you see that these new stellar to halo mass relations implied evolution, contrary to what I said before. So here it becomes really interesting because I was in a meeting like a month ago, and there was a lot of discussion about this. Some people was speculating that it should go like this. Some people were saying that there is not evolution at all. I'm saying that the evolution actually is something funny, no? Something like this. And all of this has implications in galaxy formation models, okay? You can also make these very cool figures where I'm showing the redshift, the halo mass, and the stellar mass. And the different lines that you see here is assembled as a function of mass and as a function of the stellar mass. And the color code is the specific star formation rate. The star formation rate. So then you can see the 3D phase, hyperphase of the galaxy evolution, actually. For the galaxies, this is for the galaxies that we observe today. This is not all the galaxies. This is only the progenitors of all the galaxies that we observe today. And then you can make the projections, which I already showed before. And I'm getting basically the same answer. So here is the halo mass, function of redshift, color code by star formation rate. I also get the information that most of the star formation happen in high mass halos at a very high redshift. And here I'm plotting, instead of halo mass, I'm plotting the stellar mass. And this is just reflecting the fact that in high mass halos occurs most of the star formation rate. Here is reflected in the fact that the red areas in very high mass galaxies. And here is just how galaxies evolve along the stellar to halo mass relation. If the stellar to halo mass relation was time independent, actually you will see something like a solid line. You wouldn't see this color code, okay? You can also ask whether really the galaxies and the halos are co-evolving just by dividing the specific star formation rate of the halos with the specific mass accretion rate of the halos. So here I'm plotting again halo mass, redshift, and color coding by this quantity. And you see that there is like a critical line. So this number goes from 0.02 to 10, and 1 is here. 1 is like the yellowish curve, which is actually this line that you can see here. So there is like a critical line where something is happening. We don't know what is it, but the model is telling us something. So then what we did is to plot this, instead of halo mass, we plot this as a function of the stellar mass. And then we plot the fraction of galaxies that we observe that are forming stars against the fraction of the galaxies that are quenched, or they are not forming stars. And this critic line that I was saying here, which is right here, is basically the same dotted line that is here, which is the transition between being an active galaxy, meaning that the galaxy in the halo is co-evolving, to be detached from the growth of the halo, meaning that the galaxy is quenched. Which is kind of amazing because we never put this information in the model. And you can make another very complicated figures. So this is a kind of busy figure, but the point here is that you are seeing how was the progenitors of the galaxies for the galaxies that we observe today. Here is the star formation history of the corresponding galaxies. This is the star formation efficiency of these corresponding galaxies. But actually, what I also implement was how was the growth, the rate growth of their supermassive black hole in the center of those galaxies, which is kind of the thing that is really interesting is that, so if you focus on the black line, which is the most massive galaxy, you can see that the star formation history of this galaxy goes up, then something happens, and some redshift, which is basically a redshift between redshift 3 and 3 and 4. And this corresponds to the peak of the accretion rate of the supermassive black hole, which also more or less is consistent with the fact that the galaxy there is a transition with the galaxy become from star forming to quenched galaxy. So in all this empirical modeling, we are not putting any physics, but we are inferring what are the mechanisms that are behind this. Now the next step is actually to put the real physics, no? Why the supermassive black hole should quench a galaxy, for example. Okay? And here what I'm showing is the density, the stellar mass density at the 1 kiloparsec. I'm fixing the 1 kiloparsec of the galaxy and see how the mass or the mass density inside of 1 kiloparsec of the galaxy is building for different masses. And here I'm showing another quantities which are not very important. The point here is that this is also consistent with the fact that the galaxy is becoming really, really concentrated in the center, which is consistent with the idea that the black hole is growing. Actually, the peak is more or less at the same time when this curve stops, basically. These are just examples of the things that you can do with this kind of very simple models. Again, these models don't replace the real galaxy formation models, but you can get answers about how it's like looking to the answers on the back of the book, no? When you are solving the problems of the book. You know the answer. Now the question is, how can we understand galaxy formation through these models, no? Another important point is how do we understand the the uncertainties that affect the galaxy-halo connection. What I'm plotting here is again the galaxy stellar mass function, which is always our input for for all the techniques that I just described. And if you plot directly from the tables, if you read the tables that the authors give you, and you plot all the mass functions, here I did a very big compilation of galaxy stellar mass functions, you will see that there is a very huge scatter. So then the idea was, if you have the halo mass function of halos and subhalos, and then you have the galaxy stellar mass function, and you match the two of them, you get the interface, right? That was the technique, the Bundesmatching technique. But here the point is, well, if you have this huge scatter with a stellar mass function, which mass function you should use? No? Which one is the good one? The point here is that if you make this plot without carefully taking into account the variations and the ways that people measure the mass functions, you will get an awful answer, in the sense that, for example, here, just by standardizing all the cosmology from these models, you see that all the mass functions basically stack together, showing like a very consistent evolution. And also, just by changing the EMF, including in the change of cosmology, including the variations in the initial mass function, you can see that the agreement or the consistency between these parameters are also good. Here I just put a table with how to change the initial mass functions, the offsets that you need to apply for initial mass functions in order to get a good reference frame between all of them. Yeah, this was my point. This was the point. So you always fix the halo mass function, and then if you match, you will get very different answers if you don't carefully correct for those effects. Also, there is a huge effect on the halo mass functions. So what I'm showing here is, I did this plot for just comparing how well we can constrain the halo mass function from simulations. So here I'm showing the halo mass function. So the function that is here is proportional to the halo mass function. So I will just say the halo mass function as a function of mass. 1 over sigma is also proportional to the mass. So here I'm showing the halo mass function at different redshifts and under different assumptions. So the main point here is that we believe that the halo mass function, it's a universal function that does not vary with cosmology, neither redshift. And the main point here is that if you assume that this function is independent of redshift and cosmology, you get this large scatter at some point. So here are the residuals. The light gray bands is the 5%, and the dark gray is the 10%. So if you assume that this function, which is commonly assumed in the models, is a time-independent function and independent of the cosmology, you can get uncertainties up to the 20%, as you can see here. But when you relax that assumption, you see that the errors between the simulations is around less than 5%. I would say that is around 2 or 3%. Okay? And this is just a summary of all the uncertainties affecting the stellar to halo mass relation. As I said, the choice of the initial mass function can introduce a systematic of up to the 0.3 dex, for example. The choices of stellar population synthesis model. So different groups treat different the stellar evolution. So there are also shifts that can vary from 0.1 to 0.3 dex. The parameterization of the star formation histories also varies around 0.18 dex. The dust attenuation, the assumption behind the dust and the galaxies also introduce a systematic, which is around 0.1 dex. So if you see, just at this point, seems that we don't know how to measure stellar masses, no? That we measure stellar masses with a lot of lot of uncertainties. And also the intrinsic errors from measuring the individual stellar masses, which can go from 0.1 dex to 0.15 dex, from redshift 0 to redshift 1. Also in the sample variance. So the sample variance is that if you look to some part of the universe and you were and you had very bad luck, you can look to a very high overdensity. So you will say, oh, if I measure the mass function, seems that the number density is really high, no, compared to other observations. But that was because you had very bad luck. So you were in a very high density region. So that is sample variance. Also in the way that we constrain the photometric redshifts, and well, as I said, the uncertainties in the Halo mass function and the uncertainties on the cosmology. So how do we treat this in all these models? Actually, it's really simple. The idea is, I will just schematically describe this using the abundance matching. So the idea is really simple. We know that abundance matching is this relation, okay? So if we include a scatter on the stellar to Halo mass relation, we just take this function and we convolve it with the scatter. And we obtain a galaxy stellar mass function that we will call true. This is called direct because we are assuming that this is the one, the real one, the intrinsic relation. So when we convolve this with the scatter, because we know that there is a true scatter around this relation, we can model the true galaxy stellar mass function. But we know that the true galaxy stellar mass function has a lot of uncertainties. And most of these uncertainties comes from basically from the measurement from the random uncertainties and the measurements of the individual stellar masses. So then we should convolve again the galaxy stellar mass function to get what we observed in the galaxy stellar mass function. So basically this equation summarizes all these steps. If you want to compare observations and obtain a stellar to Halo mass relation that take into account all the systematics and errors, you should convolve with all these steps, which includes the scatter of the stellar to Halo mass relation and also the random scatters and individual measurements. Okay? So here are some examples of the impact of how the true galaxy stellar mass function is affected after convolving with the random errors. So here the points are the observations. This is for redshift 0, for redshift 0.1, redshift 0.5, and redshift 1, basically. So here the red lines show the fits to the observed mass function. If you deconvolve by measurement errors the galaxy stellar mass function, but by the uncertainties that I described before, then you will see that the intrinsic galaxy stellar mass function starts to predict that the number density is lower, especially to high masses. So then you can start to guess that if you apply the abundance matching technique, you will get very different stellar to Halo mass relations. And actually is the case. So for example here, the solid line shows when you are including all the effects that I just described of the convolution. Okay? This is the stellar to Halo mass ratio as a function of Halo mass. Here the solid line is including all the effects. The red dashed line is by excluding all the systematics and errors, which goes a bit up, but including the intrinsic scatter of the relation. And the blue dashed dotted line just shows when you include the systematics, but you exclude the errors. So it seems that the intrinsic scatter. So it seems that neglecting the intrinsic scatter at redshift 0.1 seems to increase the stellar fraction, which, but within the uncertainty. But at high redshifts, you start to see that by excluding the systematics and the errors, then we'll tend to overpredict this relation. Also, there is the impact of the relation by including, by varying the the cosmology. So you can do the following experiment, for example. So let's say that you have your stellar mass function, and then you start to vary the cosmology and on the function. So you also get different results. And this is just an example of a paper that combines weak lensing, clustering, and the stellar mass function to constrain the relation. So you can see here the total errors of the stellar masses for the different redshifts. So you see that at very high redshifts, the stellar masses become very uncertain. So the takeaway of that part was, if you want to make like real interpretations of this relation, you should take into account all the systematics. And this is not a takeaway from this particular kind of models, but for every observation that you should make, you should always take into account that every measurement has an error and a systematic. Okay? And if you want to compare to some model, you need to take into account that. Otherwise, people won't believe what you are doing. Okay, so next, I just want to show you some inferences about the HODs at higher redshifts using clustering. So here's the two-point correlation function. The different symbols are different stellar masses, and they go from redshift 1 to redshift 2-ish. Yeah, from redshift 2-ish. And this is the occupational numbers. So all these occupational numbers have the problems that Peter just described before. And here are the resulting halo mass relation for these different redshifts. These are new inferences of the HOD models using more recent data. In the previous figure, what I showed was, instead of showing the two-point correlation function, the projected two-point correlation function as Peter has been showing in all his plots, I showed the angular two-point correlation function, which is basically the same definition that we've been discussing before and Peter discussed, but applied to the angular separations of the galaxies instead of the physical separations. Okay? Well, actually, the distances are removable, but that's the point. So here we showed the newest constraints on HOD, and then when you plot with the newest the stellar to halo mass relation, seems to go in the same sense that I showed. That is decreasing, but not keep like constant or increasing. And here's another paper where they combine weak lensing with galaxy clustering and the stellar mass function to get the evolution of the stellar to halo mass relation. In this case, they are plotting halo mass as a function of the stellar mass, and the different colors shows the difference, the different redshifts. And this is just for the redshift interval between 0.74 to redshift 1. Okay? So you can apply these techniques to every redshift. It's not only for redshift 1. Now, again, let me make the point again. Every time that you need to make these kind of inferences, at redshift, at redshift 0, we have a lot of uncertainties in trying to constrain the stellar masses. Now, imagine to a very high redshift. A very high redshift, some people is trying to infer the mass functions. Actually, I showed some plots of the mass functions up to redshift 10. And some people is trying to infer the mass functions of the redshift 10, but the uncertainties in the stellar masses are really crazy, like a factor of 3 or even more. So you always have to take all that into account if you want to interpret correctly your model. Always keep in mind the limitations of your model. Now, the second part of this talk it's about the question of, okay, so when I start, during my first talk, one of the questions was, if we see this very complicated evolution of the halos, and we can measure with a lot of detail of the halos, the properties, even their locations, how these properties map into the properties of the galaxies, okay? But most of the time I've been talking about only the mass of the halo. Well, I talk about the mass accretion rate of the halo, but it was a more physical motivated model. But if we want to do this very empirically, how the properties of the halos map to the properties of the galaxies without any modeling, just keeping the spirit of the empirical modeling. Well, it turns out that there is a lot of discussion if their galaxies only depend on the halo mass of their host halo or depend on other halo properties, okay? So in the next figure, which is actually kind of neat. So this is a work done by a student that worked with me in Santa Cruz. So what we did is to say, well, let's apply the abundance matching in luminosities. So we get magnitude in the R band as a function of halo mass. And then let's assume that there is not a scatter in this relation. And let's apply this to the simulation. So now the next step was, well, let's measure the abundances of the galaxies as a function of the environment and the simulation. So here in front, I don't think that you can see here the environments, sorry. But here the solid lines with the shaded areas shows the resulting luminosity functions from this experiment. Here we are going from voids to very overdense regions. And the circles are observations. So abundance matching doesn't know anything about observations. The only thing that it knows is just about the interface, the total luminosity function. But it is not expected that the trend with the environment, if you have, again, the picture of how the halos form or how they evolve, that is very complicated, why the galaxies, their host galaxies should know about that. So this is very interesting. The fact that we use this technique without a scatter or anything, and we recover the observations is kind of amazing. So here we were measuring over densities in 8 megaparsec spheres, here in 16 megaparsec spheres, and we see the consistency. We did this for the R band. We also did it for more blue bands. So this is the luminosity function, the same idea, but in the G band, and this is the luminosity function in the U band. So here we see that there is a slightly disagreement, but actually the agreement is really encouraging. So then comes this interesting idea. That let's suppose that we have observers observe the luminosity functions in the bands that are available. So here I'm plotting the Schechter parameters, if you remember the Schechter function, which has three parameters, the slope, the characteristic luminosity, and the normalization. Here's a compilation of the Schechter parameters of the luminosity function from very ultraviolet bands to very infrared bands. And we said, well, let's try to apply this technique, the abundance matching, and get a photometry catalog. And then let's evolve this as a function of redshift. What is interesting is that we can see the spectral energy distribution of the galaxies, sorry, of a given halo. So then we can also follow in the history of these spectral energy distributions. So why is this important? Because observers use this quantity to constrain the stellar masses of the galaxies. So now we can study the systematics directly into the model without applying any modeling by just running the stellar population models into this model. So here we are plotting the magnitudes, which is proportional to the flux, as a function of the wavelength for halos of 10 to the 11, 10 to the 12, 10 to the 13, 10 to the 14. And we follow the SED up to redshift 5, which are this is redshift 4.5, the greenish, and the black one is redshift 0, basically. But actually, the previous plot, instead of being encouraging, they are like a bit confusing, because we didn't know anything about the halo mass. Sorry, we didn't know anything about the other properties of the halos, and we used the halo mass, and we reproduced some observables. But then there is a lot of smart people out there, and then they ask the question, well, what happened if I just relax the assumption behind that the halo mass fix all the properties of the galaxy? This is a very funny model, which is called the H matching. So the idea is the following. Again, we start by populating our halos with galaxies using abundance matching. So then we will say, we observe that there are two types of galaxies, blue and red galaxies, okay? And let's assume that the age of the halo is correlated with the age of the galaxy. It doesn't matter too much here, the details. The basic idea is that. So then what happened when I calculate the two-point correlation function, and using this idea, I split it into colors. If you remember, I said that red colors are old galaxies and blue galaxies are younger galaxies, okay? So if we connect the history of the galaxies to the halos, what happened with their two-point correlation functions? Actually, you see that they reproduce this, which is kind of interesting. But then the question is, why, if we didn't assume this, we reproduce the mass function as a function of environment? So that's kind of interesting. And furthermore, I think I flipped the slides. Yeah, and furthermore, if you remember my lecture of the Tuesday, I show you a simple model of how to reproduce the two-point, to observe it, how to, by using the two-point correlation, to observe a two-point correlation function, we constrain the conditional stellar mass functions and the occupational, so then the occupational numbers of the halos. So we are in a situation that we have two different models. One model which assumes that the halo mass is that defines everything for the galaxy, and another model which using the properties of the halos, like their age, and connecting to the colors, produce the same result. So I think this is a problem. So we have two models reproducing the same observable. So it's funny. And then this is where you need to put more into the models to check other instances. So for example here, what I'm plotting here is the number density of the number of satellite galaxies around the central mass of this, around the central galaxy of this stellar mass. The circles, the blue circles are blue central galaxies. The black filled circles are all galaxies, and the open red circles are red galaxies, okay? So what you can read from here, these are observations, okay? So what you can read from here is that for a given stellar mass of a central galaxy, blue centrals tend to have lower satellites compared to red centrals and to the average, okay? If you plot here the predictions from the HOD model, you see that everything is going well. But actually, I just said predictions because you are constraining the HOD. So more or less by construction, you are predicting this. What happened if we attach, again, we said that all halos host red galaxies and blue halo and young halos host blue galaxies. What did we obtain? Which we call the model C-form matching. The relation inverts. So what we declare as a red galaxy now has lower number of satellite galaxies than the blue ones, which is not supported by the observations. If we do the H-matching model that I just described, at low masses, the relation invert, meaning that blue galaxies have more satellites compared to red centrals. But then it flips about 10 to around 10 to the 11 in the right direction, but it's not consistent with the observations. So then one of the questions is, well, you told us, I show you that there is that there are some suggestions about, oops, the stellar to halo mass relations are segregated by colors. That at a given halo mass, blue central galaxies live in a low mass halos compared to red central galaxies. The first assumption, if you remember, the first assumption by H-matching was abundance matching, meaning that they don't know anything about the galaxy-halo connection when they start to populate the galaxies. So what if we start by saying, well, the most massive halos that are old, we will assign a red central galaxy, and the less massive and young halos, we will assign a blue central galaxies. Perhaps this will work to reproduce better the observations. And this is this model, which basically it resembles the H matching. So it didn't work. So perhaps, so for me this is really confusing because again, we have two models that reproduce the same observable, and we are doing empirical modeling, no? In some sense. So and when you have another observable, you have that, okay, by construction this model is doing something, no? It's doing something good, which is the HOD. But then the other model where we correlate the H is not doing a very good job. Even when we start by combining these two models, we are not doing a good job. But also I show you that that you can obtain the specific star formation rates of the galaxies from the mass accretion rates of the halos, which has some information about the history of the halos. So we have a lot of histories that that they say for some part halos, the color of the halo seems to correlate with the age. The age of the halo seems to correlate with the colors of the galaxies, while others says that no. So we need more modeling about this. And okay, so I will let you with my summary, which is the empirical modeling allows us to construct self-consistent models with the data and with our standard structure formation model without invoking any physics of galaxy formation. Empirical modeling constrains indirectly the galaxy-halo connection. The other part is understanding systematic scenarios in observation is vital in order to interpret correctly results from the empirical model. And the ROC says that you can gain insights on the physics of galaxy formation using empirical modeling, but they don't replace empirical modeling don't replace galaxy formation models. Okay, and I will stop here.
Does anyone have any questions?
So the last one you show about the age corresponding to the color of the galaxy, the red or blue. So it's still open question? It's
a very open question.
Okay.
It's a very open question.
At the beginning when you start populating in the center galaxy and the satellite galaxy, just you do shuffling like. So that is like you are trying a trial and error method, or?
From the perspective of the HOD model?
Yes.
You try that. But
okay.
The thing is that the clustering of the halos depend on the formation. If a halo formed earlier, it will be
Yes.
cluster compared to a
Yes.
younger halo.
Cluster,
So
but
which
it
is
would be
called
more
the assembly bias.
cluster, but it would be more dense, right? But it will be more small size.
Will be more what?
Smaller in the radius, small size, but it will be more dense if it is from earlier. No, if,
Yeah, so here the point is that in the HOD models, you don't know anything about
yes,
the other properties of the halo. You always parameterize as a function of the halo, and the bias comes from the halo bias, from all the halo bias. But the point is that the halos, when you separate the halos by the properties, you see that the clustering also change. So for example, if you fix the mass, the halo mass, halos that collapse earlier are cluster more than halos that collapse later. The clustering is higher than the halos that collapse later. So they are using that information. In the H-matching model, they are using that information. In the other model that I discussed, I'm not using that information. The point here is that we both are reproducing the same observable. But then if you look to this observable, which is the number of satellites, by construction, the HOD model reproduces this, okay? And the other model seems to fail. But then when you try to describe the galaxy formation for a very simple picture, for the picture that I showed from the star formation rates, you can use the mass accretion rates of the halos, which has information about the assembly process of the halo. And you can do that. You can reproduce the star formation rates. It's a very confusing thing. Actually, there is another observable that I didn't show, which is called galaxy conformity, which means that if you are a red galaxy, if you are a red central galaxy, you are surrounded more by red central galaxies. Okay? If you are blue central galaxies, you will be surrounded more by blue central galaxies. This is shown here as a function of the distance and the quench fraction. Okay? These are red and these are blue. Okay? And when you look to the standard HOD, there is no pattern. Observations show this, actually. So and then in this observation, they will say that their smoking gun is galaxy conformity. But then I will say my smoking gun is the HOD. So it's an open question.
okay, thank you. Still.
You were mentioning, at higher redshifts, obviously observations. It is difficult to measure things and have accurate measurements here at low redshifts. So at higher
You start to be
redshifts,
dominated by the errors and systematics at
How-
higher redshifts, in the stellar masses, I would say, in redshifts.
yeah. So all your inferences that you have made, how is there any like coto superior? Upper limit that you can say that this model has small. It's reliable. Or at what
the point,
redshift?
actually, the point was, if you want to compare two observations,
Yeah.
you not only interpret the observations directly, you also need to mock up systematics and errors.
Yeah, no, but even though when you mock up, how reliable are they?
No, where you are comparing apples with apples, no?
Okay.
If you know what are the size of the systematics of the error bars,
Okay.
Yeah, of the errors, measurements errors, well,
Yeah, that's why
you are comparing apples
that's
with
why you
apples.
show
no? That the mass functions, if you apply these systematics,
it's higher.
it's
lower.
the shape of the mass function changes.
Okay.
And also the star formation rates, the two-point correlation function change and all that.
Any more questions? No? Okay, then let's thank Aldo again. And I think we'll have a small break before starting with the presentations, with the project presentations. 5-minute break. Sorry, the minute break.
Y ya después del coffee y todo el mundo se relaja. Okay. Explain how we are going to do this, but I'm waiting for all. Salman is not here. Okay. Yeah, but there is no coffee time now. Oscar, dile que venga si puedes. A Salman, si está afuera, que vamos a empezar. Well, I'm going to start explaining. So I think listen to me, please. So I think many of you have started working in any of the projects. And maybe some of you go further, maybe some of you just started. The idea is just that one person for each project pass to the front, explain to the others what they did. That's it. It would be very fast. It's just for checking that somebody was working in each of the projects and that all this school helped to something, like to start something in you. So who is the volunteer for the project of? I know names, so I know names that people have already worked in some of the projects, so I know the people exist. If they don't volunteer themselves, I'm going to volunteer them. So please, do it yourself. I don't want to be the bad guy here. So, we're going to start with Peter's project because he's leaving. So who worked Peter's project? Peter's project? Miguel? Could you come to the front? Okay, we have for the first. And then for Aldo's project. Aldo's project, you? Good. Ruben? Yeah, you're going to present. Then Salman's project. Fabio? I'm missing someone. Bauju's project. Baujuli project. Nobody worked Baujuli project. Really? No, come on. That is not good. Yeah, please. Yes, it's in the same institute, so please. Yes, but they are gonna present, like, yeah. Yeah, it's not you. You already finished. So, nobody? Really? Mariana Haber, I think you started. You are not here. Claudio? nobody really started to work. It's okay. No, each one choose. Come on. Well, okay. So we start with who want to start? Fabio. We don't have more time. Miguel. Matias. We don't have all the afternoon. We need to leave now. And he needs to leave, so please. You are ready. Yes? Yes, Ruben is going to start, then Fabio, and then Miguel, or then Miguel and then Fabio. But it's going to... Please come. Well, you can use my computer if that helps. What do you need? Internet? No. Just a laptop. Okay. Yeah, I know. That's right. Well, a little bit more. After the presentation, we're going to finish the event. So we're going to give some diplomas. I don't know how to say this, the word in English. Certificates, thank you. And that is all. I hope you enjoy this school. It was amazing. Te vemos arriba. Dije uno por cada quien. Ah, no, solo los de hecho, yo tengo que dejar a Peter en el porque ya se lo
Julio hizo una bonita gráfica del proyecto de Peter, pero le falta como la interpretación, entonces no sé si se lo quieran presentar.
No, ¿por qué no? Se la pasan también a Miguel para que presente una sola persona a todos.
Miguel está haciendo lo de Peter.
Sí. Véganme conmigo.
No, perdón, no es el de Peter, es el de esto.
Es este, el de...
No, el de Salman.
Ah,
el de
Salman.
variar los parámetros de la simulación.
Ok, entonces es el de Fabio.
Ah, pues escríbela, Fabio.
Mándasela a Fabio.
En el Gitter.
O sea, tú hablarías, pero no quiero que pasen todos a conectar su computadora, porque eso va a tardar mucho. Dale. Ahorita la digo.
Todo lo conecto, ¿verdad?
Detected. Is there?
No lo jalo así, ¿eh?
Pon play y ya sale.
Ok, perfecto.
Si tienes play.
F5, ¿no?
No va a funcionar. Ponle, pásalo mejor. A ver. Lo estás abriendo con la Acrobat Reader, ¿no?
No supe con qué, pero es que no lo abrí. Pero, a ver, ¿puedo volverlo a abrir con otra cosa?
Dale 2 clics. ¿Con qué?
Lo abrí con eso, con la Acrobat Reader lo abrí.
Ah, ok.
Le di 2 clics y me lo abrí.
Ok, entonces pon aquí ver, de full screen y ya te lo voy a poner. Ya. Pantalla completa. Ok, es there. Ajá. Ya va a mandarlo yo. Ujú. Your no, Brenda, look for it. Brenda went away,
Okay,
and I'm
that's
gonna
it.
go.
Okay, yeah, just
In
want to make
5
sure.
minutes.
No, no,
No traigo mi celular. Tengo que pedirle el Uber al Peter. Se me olvidó.
¿Ya?
A las 5:30. No, 5:15 se quiere ir. Entonces a las 5:10.
Se lo pedimos.
5:10.
Que imprimas lo que te dio que nos firme, porque necesitamos que lo firmen aquí.
Lo mandé, pero hay un problema con la impresora. Tengo que subir a ver qué pasa.
Subir.
Sí. O sea, yo lo mandé y hay
presto
un
el
error
teléfono?
de la impresora.
¿Nos hablas?
Pero tengo que buscar entonces el teléfono de la secretaria. ¿Tú sabes el teléfono de la secretaria?
Me sé el tuyo que...
Ajá. ¿De Mariana? Yeah, you can start. You need this. I will.
I don't have a very high, loud voice.
Okay. So.
Okay, this is the project I finished. I was working a little bit on other projects, but this is the one I finished completely, and is the Aldo's project. Here's a no, not Peter's. Here's a brief description of the project using a mock catalog obtained by Aldo using the methods that he described in his lectures, which were basically three. Pond's-Maczek technique, Halo occupation distribution, and the conditional probability function distribution. He gave us a mock catalog with galaxies with stellar masses higher than 9 to the 10 solar masses, and these stellar masses were determined using several estimators or several properties of the halo mass. And just the volume of this mock catalog was sampled in a box of 250 megaparsecs per site, and these were the main things to do. Which the first thing was to compute the galaxy stellar mass function using any definition. Also to compute the fraction of satellites as a function of stellar mass, some question that he suggested. And finally, compute plot with this mock catalog. We can plot the average mean. The average stellar to halo mass relation using some stellar mass estimator. And the M star, the Bmax to the M star using another stellar mass estimator with the Bmax. So this is a brief description of the table that contains the mock catalog. This is just a label to distinguish between a distinct halo, which is a halo containing a halo that is not contained in another halo, a subhalo that is a halo residing in another halo. The several stellar mass estimations, the positions in the sky, in the box, and these are the period masses computed using several halo properties. For example, concentration, the matter density, the critical, the M peak, which is the maximum mass created by a halo or a subhalo, and so on. Here is the descriptions, and here are, and this is the first thing that he asked us to do, which was basically plot the galaxy stellar mass function, and as we have information regarding stellar masses, the volume, and we may immediately compute the stellar mass function, which is defined like the number of galaxies per unit of volume and per unit of stellar mass bin. So I plot here several galaxy stellar mass functions using the 8 different mass estimations with the properties of the halo, and well, there are some differences. Some of them tend to be less complete or to do not have as much galaxies as massive as 9 to the 9, but they have higher, more massive galaxies. So this break, as Peter told us, well, it was erased, but here was like something that if you lack of galaxies in the stellar or the luminosity mass functions, you will have this fall, and this is because you're not counting galaxies that might be here, but this is like a complete this level. And well, was the first thing. Then was to compute the galaxy fraction and the satellite fraction as a function of stellar mass, and the satellite fraction is basically the number of satellites divided by the total, which is the number of satellites plus the number of central galaxies in each stellar in the sample. So what I did, I just made some stellar mass bins and made this fraction, because we have information for each galaxy or for each halo. We have information if that galaxy is a satellite or a central. So here is the fraction of satellites for the 8 different stellar mass estimations, and as you can see, there are some that begin to increase as the stellar mass decreases, and some tend to fall or to fall, because as I mentioned before, for some, look at the colors, well, they are very similar, like the purple ones. Around 10 to the 10 is complete the stellar mass function, so this fraction is also affected by that fact here.
Yeah, but what is the main conclusion? If you take all of the galaxies about 10 to the 10, come back to the following. If you see galaxies just about 10 to the 10, what is the conclusion? Which estimator gives more
which the log virial, the one that is determined with the virial mass of the halo, which is basically the
highest fraction of satellites?
At 10 to the 10? No, sorry. What is called? The Pmax. The Pmax and
It's BP, no?
Ppic. Yeah, I forgot to put the one of the question, and the one that is least percent less fraction of.
What is the worst?
The worst is at 10 to the 10 or in general? Is the 200.
200 the background.
The background, yeah.
The different definitions of masses could lead to differences in the fraction of satellites, no? Which will have an impact on the 2-point correlation function if you use only abundance matching. So that was the point. So then if you go to the next figure, which is the stellar mass inferred using Bmax, for example, which was the one that has the highest fraction of satellites, you see that when you infer stellar mass through Bmax at a fixed halo mass, satellites usually tend to have higher stellar masses than central galaxies. So this means that when you apply abundance matching as a function of halo mass, perhaps you need to take into account that the relation between centrals and satellites are different, no?
Yeah, and this is why it's shown here. The third thing that Aldo asked asked us to do was basically, if we have the information of the stellar mass for different estimations and the halo mass also for different estimations, using the Bmax estimator, as he said, in the stellar mass and the virial mass, compute the average MH relation, and here I only plotted with blue the total relation, with red the satellite relation, and the centrals are in open circles with error bars, and we see that there is a segregation, as Aldo said. For a given halo mass, the satellite galaxies tend to have more stellar mass. And
Than central. Yeah, and we know that. Oops, sorry. And we know that using abundance matching with Bmax reproduces better the two-point correlation function than using the virial mass, or the mass of the accretion in the case for subhalos.
And finally, this is the it is basically
this is
the same, but using the stellar mass and the Bmax.
Yeah. Okay.
Result.
So, yeah. Okay. Good. Thank you. So, who did Peter's project?
Peter's project.
Sí, te la paso aquí a los escritores. Ah. Mariana, ¿me puedes ayudar tantito? Como no tengo más, nada más quería jalarlo, pero no pude.
Ahorita no lo hacemos porque queremos que le pasen.
Ok, si quieres te lo paso ahorita por correo.
O te doy el reloj. Ok, ellos van a venir ahorita.
Ok,
Vale. Entonces, ahí está la data.
Did somebody else try Peter project, or we are the only ones that tried it?
He did, didn't he?
Peter's.
Yeah, I was working on it, but I couldn't make the plots.
Do you want
Okay. Awesome.
¿Dónde me lo pongo? No puedo hablar bien.
No, está transmitiendo, entonces.
No manches que está transmitiendo.
¿Sí?
¿Se está transmitiendo?
¿A quién le estamos transmitiendo?
No me hubieran dicho.
Okay. So this is Peter project, and we make it. Well, we did the first two steps, and we.
The last one, but
Our plot didn't came out pretty well. So, okay, let's start.
so the first thing we did in it was just the differential number counts. So we just made a little program that just
Yeah.
Is it not working? I can use Miguel as well. Okay. Yeah.
¿Es este, verdad, el primero?
No, ni siquiera está abierto. I'm sorry about that. This one's working now.
Okay.
Sorry. I don't know. Where is it? Oh, there you go.
Yeah, sorry about that. We forgot to open the first program.
And then I don't know where it is. It should be this one? Yeah, it should be this one. And then, but then we can. Was that right? Oh, okay. I cannot see anything. There we go. So if we run this code, this is a little histogram showing the distribution, the number counts per magnitude. So the thing here is we didn't calculate the volume of the survey, so that's
It's not properly normalized then.
The area, you mean?
oh yeah.
In order to
Sorry.
Okay, so we can see that using this plot, we can see that the survey is flux limited. So in order to compute the luminosity function, we have to make a better cut. Well, we have to choose a volume limited part of the survey.
And then to see where to do the cut, we used I think it is, well no, this one's in the actual
Calculador, prueba pro.
it should be this one.
The plot, that's fine. Okay.
Oh no, this is not
Okay.
the one we wanted. This is just number counts per redshift, but the should be here. Yeah, there it is. And then this is
So we computed the absolute magnitude in order to see where to make our volume limited cut. No, es eso, ¿verdad?
magnitude is a function of something.
I can't see anything.
Yeah, we're sorry about that. We probably should have.
A small question. Absolute magnitude. Are you sure you're on?
That's not the proper plot. We are trying to figure out. Yeah, sorry about that. We've lost the program that we were doing.
It's just,
We have a lot of stuff open. Sorry about that.
it's very hard to see.
Si quieres pasar, es que tú sabes cuál es. Si quieres yo lo voy moviendo.
No, no es ese. Tampoco. Tampoco. Ajá. Este es. This is the one. Yeah, but. So, there we go. Higher up. This one's the absolute magnitude in the R band versus the redshift, and here we can see how the sample is flux limited, because we can see how in the if you go to very low redshift, you have like a complete sample, but as you go to higher redshifts, you start missing all the galaxies that would appear that are in lower luminosities than, say, in minus 15s in absolute magnitude, sorry. And then what we did was we made like an artificial volume. We made a cut. We made it around minus 15 and around 0.07 in the redshift, so that we could have a volume limited survey that was actually complete, and we could compute the luminosity function. Yeah, here.
Have you by any chance used log, not the base 10, but log base E when computing luminosities?
I believe we did not. I think we used.
It's just the range is something odd with the range.
Yeah. We had problems with the units of.
No, but I'm not sure if
of the absolute magnitudes.
Because if we were able to see minus 10 object in the survey, it would be great.
Yeah.
Not just finding objects which are minus 25 that just they don't exist.
Yeah.
So there's something with the x-axis which has the y-axis something.
Yeah, we noticed that, but we were trying to. We thought at first it was a problem of units, because we were using the absolute magnitude with the K correction. We were using one that was supposed to have the luminosity distance in parsecs, and then we turned that into we turned our luminosity distance into megaparsecs, and then the absolute magnitude just went flying up all the way over to like minus 80 or something, which was completely
So I
not
think
making
the expectation
sense.
should be that the number should go typically between -15 and -23.
Yeah, that was what
Yeah.
we
There is
were.
some.
We definitely have a unit problem. We just couldn't find it on time. We were trying to do
But
it.
it's good to. That's the thing I want to make sure that you're aware of.
Yeah,
No, we are definitely
we were
aware.
fully aware, but we couldn't find a way to solve it. But anyway, we made that cut to make the survey like volume limited, and so that we could extract a luminosity function that made sense, and wasn't like if you didn't do that like this. You see here that you see the trend that the luminosity function should have, but if you don't make the cut, at least in redshift, you start getting a downward trend over in this side of the
What's on the y-axis?
it's the number counts again.
That's the luminosity function. So it's luminosity against number counts of luminosity. And again, it is not.
The axis is
There's no
we cannot see the
normalization.
axis.
okay.
Yeah.
Because I can't see the y-axis. Is it in linear scale or log scale?
No,
It's in log scale.
Okay.
Let me.
So I just think some of these things will be solved once you get to the luminosity right. There is something.
There is.
But it's okay.
Did you divide it by the volume?
I know.
There's something odd happening here. And I think it must be related to your luminosity problem.
Plus, we
Yeah.
haven't divided by the area, so.
Yeah.
So then we were trying to fit the Schechter function, but we were having trouble with that because we used an estimator that Python provides, but
We couldn't calibrate it properly.
yeah, it wouldn't move the parameters at all. Any parameter you gave it, it would just like as an initial guess, we set up
It
some
will give the
parameters.
initial guess and it wouldn't fit anything. So we were doing something wrong and we couldn't figure it out. That's what we were trying to do right now.
But you might consider to make your beans bigger because they should.
It looks very noisy.
Yeah.
Okay.
Okay, thank you.
The thing is the points are going up and down. And if you're plotting the number of objects, to some level, do you know what the error should be on these points?
We were expecting to get that from the feed because it also tells you the
Error on the measurements of these data points.
Oh, you mean if we
Oh yeah, exactly. If you have
computed a
observed
scatter or
this-
something like that?
You have observed this, you have this point, you measured there was like something like 0.8 and these 3 points following each other, just looking at that one. That must be about 5 objects contributed to those bits.
Okay.
Yeah.
So what's the errors you would need, because that needs to be accounted for when you do the fit.
No, we didn't compute it any error.
No, but that's something, again,
Okay. Well, thank you. And that's pretty much as far as we got, so it's not
I don't
much.
know
But
if you made it any further.
No, actually,
But I think it's
I
hard
didn't
to
plot anything. but
discuss
Oh,
it
okay.
until you have a comparison.
Yeah.
This is good.
I made it.
Well, thank you
So
very
that's
much.
pretty much what we managed to do. Thank you.
Nos pasemos a hacer el ridículo.
¿Ya ves lo que nos haces? Me muere de risa.
Sí, pero ve tu llave para otra cosa.
Ah, pues está. Pero vamos luego.
O yo.
Sí, para acordarme porque son solo.
¿Te urge o puede ser mañana?
No, para que sí, mañana.
Vale.
¿Le entra esta?
No.
Necesito mover esto. Porque no tengo. Así voy a ponerme. ¿De verdad?
Así voy a imponerme. Pero te quieres enchufar primero, ¿no?
Sí, obviamente. Me iban a enviar un correo, pero no sé quién me envió un correo. Sí.
¿No? Toma. Y es eso. Sí, dáselo, Fabio. Hola. Bueno.
Probando.
¿Y? ¿Probando?
¿Cómo funciona
Mejor con el micrófono, ¿no? Para evitar.
Sí, mejor
Para evitar feedback.
Ya va.
Él sabe cómo
Sí,
operar.
ese podemos no usarlo. Está bien. Sí, tenemos dos, digo, con eso es. Dice, no hay señal.
So, why? So, our speaker is leaving now, so let's thank Peter for the last time and say goodbye. We have a certificate, but there is a mistake in your name. I'm so sorry. You are going to take it like that. So, where is the certificate? You have it? I'm really sorry, but we are not used to non-Mexican names.
Thank you very much.
Peter.
So,
Okay.
you can go ahead with the project.
So, this is a team consisting of Fabio, Claudio, Irvin, and I, Miguel Raz. We are going to be describing Salmon's project. Can you scroll down a bit, please?
Yeah, but there's more people working on this.
Yeah.
So you should raise your hands if you're working in this project. So yeah.
Big shout out to everyone that helped with the collaboration throughout the school. And
Yeah.
setting up the GitHub was definitely a big plus for all of us. So if you contributed, good job you. Okay, so these are the specifications. You probably know them by now, but still, we were expected to plot the power matter spectra for different sorts of surveys and check what the degeneracy conditions for the parameter space were, and to analyze the different ranges for which an analysis could be carried out, and then to analyze the sensitivity of it. So to check if you fixed a set of the parameters and wiggled another one, how much would your model change by, and what this sort of wiggling would mean in terms of the reliability of these surveys and what we could learn from them. So,
Yes. So first, you can go to the GitHub and you can find there the solutions to the project. It's not complete, and for several reasons. First, we didn't know how to do everything. And the second part is some part of the code didn't work until today. So but it is here. So I'm going to explain you piece by piece. When you go here, you'll see what you have to do. And then you have some instructions to install the emulator, the things Dr. Salmon spoke today. So you can see here, this is the main web page. You need GSL, but be sure where you install GSL, because some of the codes are really tricky to install. Okay, there's some little explanation on how can you install GSL here. Okay, and how to compile the code. This is the main code we use was Frank Imu. Okay, so in the end, it's only you have to type make and just run imu.x. And so in order to do this, we arrange some things and change the code. Some parts were done by me, some parts were done by Irvin, and this is what we got. Okay, when you go to solutions, you're gonna see first 3 tarballs. In these tarballs, you have everything to compile the code and make it work. Just download it, tar-xvf, and you will go to go. So in the first part, you have IMU. Okay, so let's start with this. you see, you have everything here to compile the code, and this is the text file created by the creators. Okay, so you cannot run the Python notebooks in GitHub, so I'm going to change to my local, and this is the beginning. Okay, so you have everything. If you have installed Conda, you're good, because this is all from Conda Python. Or just install matplotlib, and you have to install pandas, and that's it for running this code. This is just something to make everything look like LaTeX. And in the code, when you enter the code, it will ask you, so do you want to use age derived from CME constraints? So you will have to enter all the parameters, but you don't have to enter age, and the code will calculate it for you. So that's the first part. Yeah, age not. No, it's age not. Yeah, it's age not. So we just read the data using pandas. In the code, I'm going to show you a little, where's the code, please, Claudio? Yeah. So, wait a minute, please. Where is this? This is in IMU. So, we changed the code because in the beginning it was really long to enter every piece of information of every one of the parameters. So now when you enter, it will ask you, so do you want to run for WMAP 7, WMAP 9, or Planck? That's it. And you just type 1, 2, or 3, and you have everything to go. Okay? So when you do that, I'm going to run it here. I'm just going to run this. It will import everything, read the data, the data from WMAP, WMAP 9, and Planck, and just change some things to make it really easy to plot. And we have it here. So this is the power spectrum against K, and you can see a small differences between the three projects. So you have, the thing is we don't have an analysis, like a complete analysis of why this is like this. Maybe Dr. Salman can explain a little bit more what's the difference between these projects. I think it's not that easy to understand. And without constraining the H naught, you have, because these H naughts that you have here are calculated by the program, by the emulator. But if you go here, you have to enter the H naught that was used for the project. It's different between Planck, WMAP 7, and WMAP 9. So this is the same thing. Just read again. This is different. You see, it's different. You just do it again, and you plot it. The difference is like nothing, because the code does a really good job trying to get the H naught for you. So, but there's difference if you go really close, because if you have this extension to the matplotlib, you can just do this, and you go. And maybe if you are really, I don't know, yeah, maybe. So you can see some differences if you do this again without the H naught constraint. So this is the first part that we had to do. If you see here, it was only to, again, okay, I have here, plot the mass power spectrum for these projects and see what the differences are. So the next thing we had to do was try to figure out the inerrancy directions for the parameter space. Dr. Salman said, okay, so in a way to do that, just try to fix all the parameters and just change one. And you'll see how changing one parameter could change the power spectrum. Okay? So this is part 2 of the solution. We'll go here. Okay. Okay, this is the sensitivity analysis. It's not complete, but this is as far as we got. It's the same again. You import everything here, but this code is different. This was done by Irvin, and if you go here, okay, school, projects, beep. So that code, it is in solutions, PKM. So, because we had to change one parameter and not the others, we had to figure a way of not doing that by hand because it will be really long. So, this is not the perfect code because we have 2 days, but so now it'll ask you the same thing. Okay, so you want to use Planck, WMAP, or W7. For this analysis, we only use Planck. And it will fix things for you, but you can choose. So what do you want to change? It will ask you that, which parameters you want to change. So you choose omega B or omega M or NS or sigma 8 or just W. And the code will run a for loop to do that for you. So in the end, you'll have first your Planck data. Your Planck data is the one we're using to compare, to see, okay, this is Planck, and this is the changes in Planck. So if we change this, what happens? So we first just read this Planck data was constructed using the EMO code that we changed. Okay, so first, and this is not the previous way of doing this. The good way would like to be having one file and just reading for that, but we didn't have time to do that, so we run each parameter 10 times between the minimum point and the upper point. Okay, so you just read the data and just change some things here, and you can plot the data using matplotlib again, and this is what you see. This is for omega B. Okay, you don't have that much difference as we expected. Okay, this is the best plot we have. We don't have this for everything. This was really long to do. So just imagine every plot is like this. Okay, okay. You just have to picture it in your head. So this is the comparison. This is really easy. What we had to do is like, okay, so we have a data frame that contains the data we have, and we want to compare it to Planck. Okay, so what we have to do is divide the second column, that is the power spectrum, and you just got this. See? So the line in just here, like in the center is Planck. And you see there's not that much difference in omega baryonic, okay? So this is PK over PK Planck for omega baryonic. The other things will show more difference. Omega matter, you have everything again. And this is omega matter. Okay, so you see differences here, okay? In the left part of the PK. And if you compare with Planck, this is what you have. Okay? So you can see there's differences. And the thing is, what we have to do here is like trying to see if we change one parameter and we change another one and the results are the same, these two parameters are correlated. Okay? That's the thing we have to see. Now, we change an S. It's the same thing again. Okay, this is changing NS. Okay, it's similar. You see, it's similar to omega M, but it's not the same. Okay, this is the differences. Again, the line here, the right line here is Planck. So, a little more. Changing sigma 8. You read the data, change columns, and you plot. This is sigma 8. You see there's more difference here. And you will have to see that here in the plan comparison. And you see it here.
What is that? Is that NS?
No, that's sigma 8. Sigma NS was before. And in the end, it's just W. We know W is really close to -1, but we still want to change it. So, again, you plot the data, and you find this, not much difference. You don't see, the thing is, we did the other plot as a suggestion from Dr. Salman because it's not really easy to see here the differences. Okay, but when you do this plot, yeah, you can see some differences. And the other part of our project was trying to compare this and trying to calculate here, trying to compare the power spectrum to measure the galaxy bias. But the thing is, the code that was provided for the authors didn't work until today, so we didn't have time to do that. But I think this is a really good example that what Dr. Salman showed us today, that you can do really fast analysis and check without running big simulations, change your parameters and see what's happening with your simulations. Of course, this is not complete. We have to do a lot more of analysis, but this is a beginning of some really good work. You have all the instructions to follow these notebooks and to follow these codes. It's really easy to do. They just have to download the repo, and you have everything to do. So, thank you.
Okay. Thank you.
Keep collaborating. It's up there.
Well, just to mention that there is another group that also worked there, Salman's project, and have some plots, but it's already too much time. But they can get up and say, yeah. Also, yeah, thanks to them. They're gonna set the plots, and we are gonna put them also on the wiki. So I'm pleased.
Oh, sorry. First, please, all the other groups send me your slides and everything. So there's the project and solutions in the GitHub for everyone can see them. Please.
I also got my book, so
Yeah. Thank you.
the idea would be also to continue this so that any other person who wants to use it, all the work we're done, and we have.
So. Okay. Well, you can ask later. Okay, let's finish this. So we have the diploma, the certificate for Salman. So okay, thanks for coming. We have also for Aldo, so thanks also for a great course. So I'm going to put on a slide just to thank many people that help for doing this. As you can imagine, it's a lot of work, so I don't want to pass this. It's the last slide, so just wait, and then you have coffee, and we finish, and you can go. You are free, finally. So, Miguel and Matias have all the certificates for all others, so you can pick them with them. And then, it's because I want to do that fast that is not working. It's there. So, I lost the mouse. Do you see the mouse? Well, I can figure out. So we need to thank all the people of service that they help us to have coffee and all the lunches there. So Ernesto and Jose Luis, The internet connection maybe was not great, but thanks also to Neftali, to the photographer that has a lot of picture of us, so it will be somewhere and I can pass to everyone. Javier and Alberto, the audio and video. Maria Luisa and Lisette that print all your gaffetes and your certificates. It's a lot of work also. All the posters, the communication, internet, all the students that help, were always working here. All the chairs, Mariana, Alejandro, Chandrachani, Brenda, Oscar, Matias, Miguel, all of them help a lot. Fabio and Miguel that set up all the hip-hop staff. Claudio also, so thank you everyone. All the organizers also help, they are there, so who are there? Jorge Cervantes, Axel, Mario is somewhere there, Octavio should be also there, so, and Gustavo Liz that should be also there somewhere. And all the institutions that finance this event, so I hope you enjoy.